Science that's cool, papers so unique.
Welcome back to
Cool Ass Papers that I read this week.
What's up, nerds? Did you know that you could make the same cell either good or bad with yeast? I'm Matty C, PhD in chemical engineering. I break down scientific papers in a way that you and Nana can understand. And I swear, the more that I read, the more I'm convinced that science fiction is just becoming science. Like in today's paper out of my old lab from McMaster University, Modulating pro-fibrotic macrophages using yeast beta-glucan microparticles prepared by pressurized gas expanded liquid technology. Look, I know that was a lot of really big nerdy words, but please stay, please. The gist is that they made microparticles to change disease causing immune cells into disease treating immune cells, specifically to make damaged lungs healthy again. Now, when you hear this, you might be thinking something along the lines of, oh wow, that sounds just like modern medicine in the year of our Lord 2025. And you'd technically be right, except in this paper, they don't use any medicine. They just take components of yeast, yes, that yeast, do a little hey how are ya, and then treat the lungs. But like most papers, the beauty's in the details, and there's a lot of details here. So let's get into it. There's a few separate topics we need to go over before we link them all together. And here they are. This covers topics from biology to chemistry to immunology to engineering, but don't be scared. Luckily, these authors did a masterful job of taking all of these topics and combining them into one cohesive story. And now it's my job to try and not it up. Let's start with interstitial lung disease. Interstitial lung disease is a blanket term that describes heavily damaged lungs. In most cases, the lungs are so damaged that they form thick scars. The scars are so thick that they make your lungs hard, which in turn makes it hard to breathe. Lungs work best when they're a little bit elastic. The scarring is called fibrosis, and the lungs are said to be fibrotic. Keep these specific words in mind because I use them interchangeably throughout this video, but they mean the same thing. Fibrosis means hard lungs, means bad. Though there are FDA-approved drugs to treat lung fibrosis, they typically need a very high dose to work, and they come with a lot of side effects. For this reason, researchers have been trying to develop a new wave of medicines that works better and have fewer side effects. Next, we have macrophages. These are types of immune cells that have very different functions, but for the sake of this video, we're only going to talk about how they function in the lungs. You see, macrophages that are located in the lungs have two main states. They can either be M1 or M2. Both of which have their different functions, and they're listed at the bottom of this image. M1 macrophages are said to be pro-inflammatory, meaning that they recruit other immune cells to help fight some kind of infection. M2 macrophages are the opposite. They're anti-inflammatory, meaning that they stop inflammation and start to remodel the lungs to make them stronger after fighting an infection. The problem is that as M2 macrophages heal and remodel the lungs, they inadvertently cause this scarring that is what causes fibrosis in the lungs. M2 macrophages are also called pro-fibrotic macrophages, or macrophages that cause fibrosis, and M1 macrophages are anti-fibrotic ones, meaning that they remove or prevent fibrosis. So for the sake of this video, for the sake of this paper, M2 are the bad guys, M1 are the good guys. So if you're getting the vibe that macrophages are a little bit two-faced, it's because they are. Now, it all comes from a good place. They don't mean to talk about you behind their back. It's what happens accidentally when they're trying to help. But there's a good thing about being two-faced. Maybe I shouldn't say that. They're not always one face or the other. They can switch from being bad to good. And this is where yeast gets their time to shine. Yeast beta-glucan, or YBG, is a polysaccharide found in yeast that provides structure to yeast cell walls. For the sake of this video, that's not super important. What is important is that it has an unbelievable effect when it interacts with M2 or bad macrophages. When YBG binds to a specific receptor on the outside of M2 macrophages, the M2 can become M1 macrophages. Remember, these are the good ones. So wait, hold on. If we can take bad macrophages and make them into good macrophages, why don't we just add a butt ton of YBG until the healthy lungs are better? Natural YBG isn't very effective. As the authors state, there's an inherent variability that comes with YBG, meaning that the size and shape isn't always the same, which likely affects how strong and effective this binding is to those evil M2 macrophages. Specifically, making microparticles from YBG, which are bigger and more organized versions, have been really good at making M2 macrophages glow up into those M1 macrophages. So taking all this together, let's make a game plan. We simply have to make an ordered, nice microparticle that hates to be in order and nice, and then add them to damaged lungs so that they make the bad macrophages into good macrophages and make sure that the lungs become healthy again. Easy peasy. Every good game plan needs good execution, and in the world of science, that means good data. The first thing they had to do was make microparticles and make sure they looked the way they wanted them to. They used this technique called Pressurized Gas Expanded Liquids, or PGX. Yes, another acronym, but I promise we're almost done. It's a proprietary method, so I don't have all the details, but it's basically a way for a YBG in liquid to become dry while under a very specific environment. As it dries, the YBG becomes a microparticle with a consistent and predictable size. If you're really interested in the details and care at all about how this method, which involves supercritical CO2, whatever the hell that means, is better than current methods, I'd recommend reading the full paper. But what is important is that if you have a predictable and consistent particle size, you're more likely to predict and have a consistent effect in biology. And here's what those microparticles look like. God, they're beautiful. Detailed microscope images of particles are always my favorite part of any paper because they just look so good. Like these images are just so crisp. But anyways, here we have YBG microparticles made in 3 different ways. On the left and center, we see YBG particles made with the industry standard process. They have slight variations that aren't super important for this video, so just know that both of these columns are the industry standard. On the right, we see YBG after using their fancy PGX process. And you might notice a few things. One, the ones on the left are bigger and they have more of these weird creases. Especially the one on the far left, it kind of looks like a cartoon rendition of someone's brain as it melts. On top of that, the particles in the background have slightly different shapes than the ones in the front. And 2, the ones on the right are much smaller and are very, very consistent. They're all basically the same size and shape. They all kind of look like those cute little pebbles that you can skip at the beach. Don't believe me? This graph shows just how consistent the microparticles are. This green curve represents the sizes of their fancy particles made with PGX. All of the particles are between 1 and 10 micrometers in diameter. But the other stinky standard ways of making particles, shown in red and blue, are all over the place, ranging from about 10 to 200 micrometers. And you can see that they're inconsistent based on the multiple peaks. Multiple peaks means inconsistent, single peak means consistent. And this graph here shows how many pores are inside each particle, where the higher number means more pores. This isn't super important yet, we'll get to this more later, but just note that the PGX particles have the highest number of pores, whereas the 2 stinky standard methods, shown in blue and red, have much less. Even though these all use the exact same source, they're using the exact same yeast beta-glucan or YBG, the methods used to make these particles will change its size and shape drastically. It's important to remember that particular size and shape will have a particular effect when put in the lung. And that's pretty cool. Now this brings us to their next experiment, where they wanted to see how each of these particles behaves in different cells. So they added their microparticles to a plate full of macrophages and wanted to measure how much they bind to dectin-1. This is a specific receptor that makes macrophages go from stinky M2 to yummy M1. The higher the curve, the more binding that happens to this game-changing receptor. The PGX microparticles, shown by this green curve, bind significantly better to this receptor at every microparticle concentration that was tested. We're talking anywhere from a 5 to a 15-fold increase in the binding compared to the other microparticles made with the bad traditional ways, which again are shown in red and blue. They attribute this higher binding to the size and number of pores in these microparticles. They didn't believe me, but I told them it would come full circle. And it's well known that more pores means higher surface area, which means more points of contact with that dectin-1 receptor. This is just the tip of the iceberg, because even though they prove these specific microparticles can bind to this receptor more often, they still need to show that it actually changes macrophages more. And this is where we get to my other favorite experiment of theirs, precision cut lung slices. They took lungs from mice and kept them alive in a test tube in the lab. Then they took small sections of these lungs and measured how many M2 macrophages were present. It's pretty common for scientists to use cells grown in a dish or grown in a test tube to make their experiments, but you're only looking at one cell type that's optimized to grow in these conditions that aren't very realistic. But by collecting these lung slices, you get to take pieces of a whole tissue. A whole tissue has many different types of cells, including different types of lung cells and different types of macrophages. What's also important is that all of these different types of cells are always talking to each other and influencing how they behave. I guess our cells really aren't that different from high school kids. This was the moment we were waiting for. After collecting these slices of lung tissue, they wanted to see if their YBG microparticles could change M2 macrophages into M1 macrophages. Pay very close attention because there's like a billion graphs that all look the same and they are wildly unsexy at first, but I promise they'll look beautiful in a minute. Here's an example. You see what I mean? Yeah. Anyways, let's start with the x-axis because it looks kind of funky at first. So these researchers use cytokines. They tell certain cells to act and behave a certain way, and these are meant to transform any macrophage in the lungs into a bad M2 macrophage. A plus sign means that they added these macrophages into this specific group of tissues, and a minus sign means they didn't. And below that, there's another friend, which represents how many of these YBG microparticles they added, whether it was 0 up to 1,000 micrograms per mil. The y-axis shows us how many M2 macrophages are present in each scenario. The higher the bar, the more M2. This white bar, for example, has nothing in it, so there are very few M2 macrophages. The black bar is the opposite. They added all of these cytokines and nothing else, so we can see that there are a lot of M2 macrophages. But notice the right of this black bar. After we add PGX-YBG, the bar shoots down, meaning that we get way fewer M2 macrophages and are likely seeing these M1 macrophages. Wow! Look, I get it. Some of you are probably thinking, oh, it's only one graph. You shouldn't be so impressed with just one. They saw similar results with slightly different cells here, and all of here. They even looked for markers of M1 macrophages here. Pretty impressive if you ask me. All right, that was a lot of gray, but what does it all mean? The authors have several key findings that they'd like to highlight. One of my closest friends, Nate Dowdle, was one of the main authors on this paper. Here's what he had to say. The paper really highlights how different processing methods can affect the physical and biological properties of these materials. The PGX process is really interesting in that it's relatively simple, scalable, and much better at preserving the inherent particle properties of YBG compared to conventional processes like spray drying, which means more effective and reproducible immunomodulation. That's just a fancy word for changing M2 macrophages into M1. There's definitely more work to be done, especially in determining its efficacy in fibrotic animal models, basically meaning that they need to do this in living things to see if it works to the same degree. But I think the most exciting future application is the inhalability of these particles. Follow-up paper coming soon, which would allow for direct access to the lungs and help mitigate some of the nasty side effects associated with current anti-fibrotic drugs. Right off the bat, we definitely agree on all of the main things and how impressive this paper is, but I thought it was interesting that he really focused on the importance of the PGX process. That was kind of the part of the paper that I didn't think was as cool, but it's even cool to see that people with similar backgrounds have very different takes on what is the important parts of any paper. Now, I'm a little biased because I watched this paper being developed over the last 5 or 6 years. But even that aside, it's still really impressive for a number of different reasons. As a particle nerd, I love how they were able to design a particle in a certain way based on how they expect it to treat a certain disease. I was also so impressed at how many different topics they covered and how they're able to put them all together into one story. I think it also shows the importance of collaboration. You have certain authors on here who are very well versed in the biology and the lung side of things, and others who are purely nanotechnology experts. But they came together and made it work beautifully. And finally, I think treatments like YBG are really important for people who want treatments that are sourced naturally. This will likely ease the mind of people who are considered pharmacophobic. These are people who are afraid of pharmaceutical drugs. Some studies even report that up to 20% of people are pharmacophobic, which will prevent them entirely from taking the medications they need to make them better. Some people might hear that if a treatment is sourced naturally, there's less to be worried about. If you learned something today, give this video a like and consider subscribing. Come on over to Instagram and TikTok where you can get paper breakdowns in bite-sized form. And if I missed something, let me know down below. But with that, see you later, nerds.